All right, how's it going? Welcome back to another video here in the series on linear algebra. Admittedly, I've taken a little bit of a break from making videos. I think it's been a little over a week since I've posted the last one. I have been on vacation for the past week, but nevertheless, I am back now and I'm more than ready to be making videos again. Very excited to be doing that. And really, it feels like what a point in the video series to be ready to just take that slight break. Because if you haven't been able to tell by the title of the video, we are going to be talking about matrices in this video. And that's kind of like the central object that people think of when they think of a linear algebra. You're working with matrices, and also it tends to be one of the objects that is most confusing to people when they start to learn linear algebra, especially if the background, the proper framework for understanding matrices is not established. So my goal in this video, there are two main goals. First is to describe what a matrix is. So just to answer that question, what is a matrix? And then second, to get an intuitive understanding of what a matrix is whenever we look at a matrix. So in other words, if we were to look at one, we would say, okay, well, what does that mean? And how can I think of it intuitively rather than just the literal object on the whiteboard or the piece of paper? Okay. So kind of an ambitious goal, but it's one that I'm definitely excited to take on, and I hope that you're ready to do that as well. Now, in order to do that, I want to really emphasize the concepts that were introduced in the last video when we talked about linear maps. If you've noticed, and if you've taken courses on linear algebra before, or familiar with linear algebra, you might have heard that matrices are these foundational objects, but it's been at least over 10 videos now in the video series, and we still haven't talked about matrices. The reason for why that is because we've been trying to develop a lot of the necessary framework to understand matrices in an intuitive way, as opposed to maybe some courses which just throw these things out there called matrices, and then students have no idea what these things are and how to intuitively understand them. So because of that, especially the last video, that is kind of the background, the necessary framework that we need in order to understand what matrices are. So just really quickly, let's go through what we talked about in the last video. So in the last video, we talked about these things called linear maps, and we could describe a linear map. I'll denote it as M for map. And we said that a linear map was a function that mapped between two specific types of sets, which were vector spaces. After all, linear algebra is the study of the algebraic object, the vector space, right? So here, the domain V is a vector space, and the codomain W is a different vector space. And it is not just an arbitrary function, but it is a function that has this specific property. It is a function that if it were to take a linear combination of input vectors, or in other words, some scalar times a vector plus another scalar times another vector from the domain, it will spit out a corresponding linear combination of vectors in the codomain. So essentially we could pull out the scalars, and then we can distribute M across each of the two vectors, kind of like this, right? And we described in the last video that we were interested in linear maps primarily because it was a function that preserved the axioms defined on a vector space, and specifically how the operations are defined on a vector space, right? We showed how it preserves vector addition and scalar multiplication. So this was very much definition-wise what we established in the last video. And then for our intuition, we said we could think of a vector as an arrow in space, and a linear map is an act of moving that arrow in space in some way, shape, or form. And if a linear map acts on every input vector, you can imagine in your starting vector space, if you have an arrow pointing at every direction in space, that map, M, will move every single one of those arrows in space in some way, shape, or form. It might rotate them, it might make them larger, smaller, it might reflect them across a certain axis. There are different ways that a linear map can manipulate or change or transform a vector. So that was kind of the visual, intuitive, dynamic picture that we tried to describe, at least. Okay. So hopefully all of that makes sense, and hopefully that sounds familiar. Now, what I want to do first is to answer one of the first of the two goals in this video, which is to say, what is a matrix? And with everything I've just said in mind, let's take a closer look at this general picture that we've established so far. So in the last video, again, we said that V and W were vector spaces, but we kind of just said these were arbitrary vector spaces. But if you remember, what we've been saying for this class is that because this is just the introductory linear algebra course, we can, for all intents and purposes, think of a vector space as some version of Rn, whether that's R2, two-dimensional space, R3, three-dimensional space, where you can have n be some positive integer, right? So let's do that. Rather than calling these V and W, maybe let's try to keep this as general as possible, but restrict them to the various types of Rn vector spaces. So maybe for the domain vector space, I can call it Rn. And because before we said V and W didn't have to be the same, they could be different vector spaces, I'll call this R, but I'll give it a letter M, where M might not be equal to N. It could be, but it doesn't have to be in the general case, right? So these would be the two, I guess, most general types of vector spaces that we're primarily interested in this video series. So we say, okay, this is good. We're getting a little bit more concrete, not just looking at these arbitrary vectors, or vector spaces, I should say. But now let's try to imagine what is actually going on when M acts on a vector going from this domain into this codomain right here. So if M acts on a vector in Rn, let's imagine what is going on here. So we think of M as a function, and rather than just using notation, like just using V with a little hat to denote the vector V, I want to actually write out the column vector in Rn. So maybe this vector V, and let me do this here. We'll say M acts on a vector V, but if we were to write V as a column vector, it would have components V1, V2, all the way down through V sub n. Right? If we're working in n-dimensional space, then the vector will have n components to it, like this. So M takes in this vector, and it needs to spit out a vector in the codomain, or in other words, an m-dimensional vector. And to make sure that we're not confusing this vector with the codomain vector, I don't want to call the codomain vector V as well. Right? That would get confusing, and after all, they're different vectors. So maybe I'll say that let's write this over here real quick. Let's say V is in the domain, Rn, and maybe I'll just denote another vector, W, in the codomain, Rm. And we have the property such that, let's do this, that M takes in V in Rn, and it maps it to W in Rm. So M of V equals W, like this. Now, how do we take this compact equation and write it out over here? Well, if this is the column vector V, then it's going to map to the corresponding column vector W. And the column vector W is going to have components W1, W2, all the way through Wm, rather than n, right? Because m is the dimension of the codomain. So this is a little bit more specific of a picture that we're going to be interested in this video series. And what I'd like to do now is, because after all, this section is on linear maps, so what we're really interested in is the content of M, how we can look at M and understand this function that takes in V and spits out W. Okay. Now to do this, I want to just quickly take us back very quickly just to arbitrary functions. And this would just be like a function maybe from one set A to another set B, and F maps between them. And maybe just to keep this simple, we say 1, 2, 3, 1, 2, 3, and 1 maps to 1, 3 maps to 2, 2 maps to 3, something like that, right? So this would be an arbitrary function, but what was one property associated with a general function? Well, one of the things required by any map or any function is that every element in the domain needs to map to a single corresponding element in the codomain. So another way of saying that is that whatever codomain element that gets mapped to, any element in the image is another way of saying that, that has a specific corresponding element in the domain, right? And I guess in this case, every element in the codomain gets mapped to. So in this case, 1 specifically got mapped to from 1. 2 specifically got mapped to from 3. 3 specifically got mapped to from 2. This should all be clear, and we might be saying, okay, right? But what I'm trying to say is that whatever elements get mapped to in the codomain, it was very dependent on what element was getting mapped from in the domain. So what that means is that every element that gets mapped to in the codomain, every element in the image of our map, has a very specific dependence on what this vector v is. And if v has n components, in the general case, every component of here should get affected based off of whatever these components are. Let's say we're working in R3. You can imagine that if we have a vector 1, 2, 0, that might map to R2, and I don't know, that might map to 3, 3, 0 or something, I don't know. And this would be very different if I just changed one component, 1, 2, 1. Just because I changed the bottom component, that doesn't mean that only the bottom component of here changes. It might very well be the case that both components change. Every component in the codomain is very dependent on every single component in the domain. I hope that makes sense. That because every part of this is important, whenever we're looking at any component in the codomain, we have to understand that they are all, in the general case, going to be affected by every possible component in the domain. Each one of these numbers is important in affecting what it spits out. Haven't said too much, but I want to make that clear. That is going to be the baseline for what I'm about to write. So if that doesn't make sense, maybe go back and try to watch that again. I really hope that does. Now, assuming that does make sense, what this is telling us is let's say I want to look at this component W1. I want to figure out what W1 is. W1. If W1 depends on every component of this input vector V, we can ask ourselves, what is the most general way W1 could depend on each of these components right here? And I guess that's an interesting question to ask. But let's keep in mind that we are working specifically with linear maps. And linear maps often involve linear combinations. After all, that was how linear maps were defined. A linear map will take a linear combination of inputs and spit out a linear combination of outputs. So the most general way that W can depend on each of these components right here is through a linear combination of these components. Let's see what that looks like. Well, a linear combination of these n components we could maybe say is A1 times V1 plus A2 times V2 plus all the way through A3 times V3 plus all the way through AN times VN equals W1. Where A1, A2, all the way through AN, these are just scalars, right? These would be the scalars in the linear combination. So we can think of those as real numbers. All right. So we say, okay, good. W1 depends on a linear combination of every component in the domain vector. Now let's do the same thing, but for W2. How does W2 get affected? And if we understand that principle, that every component of here, in the general case, gets affected by every component of here, then W2 can also be written as a linear combination of the input components. So let's do that as well. So I'm going to write V1, V2, plus Vn. But I want to ask the question, do we think it's going to be the same linear combination? And hopefully we can immediately see the answer that's going to be no. Because after all, if we had the same linear combination, if we had A1 V1 plus A2 V2 plus A sub n V sub n, then this would have to equal this. Or in other words, W1 would have to equal W2. But we know vectors don't necessarily need to have any two components be equal, right? We could have one here and two here. So the second component, even though it's written as a linear combination of the domain components, it will be written as a different linear combination than this one. In other words, we need to rewrite different symbols for each of the scalars in the linear combination. So rather than A's, let me maybe write B's. So maybe this is B1 times V1 plus B2 times V2 all the way through Bn times Vn. And this linear combination right here produces W2. And you can imagine we could repeat this process for every single component in the codomain. So this would keep on going all the way through the final component, which you'd say the mth component of Wm. And every component of W would have its own respective linear combination. So Wm would also be a linear combination of the V's, but it would be different from each of the other ones. So maybe it'd be C1 V1 plus C2 V2 plus Cn Vn, like this. All right. Hopefully this makes sense so far, and that we're still following up until this point. Now, let me just pose this question real quick. The examples that we've been working with typically so far have been relatively small values for n and m. Maybe we're working from R2 to R3, R4 to R7, R6 to R2, or something along those lines. But n and m could be any positive integer, right? This could be R a million to R a billion, or vice versa. And you can imagine if I have a billion different components in my codomain vector, if I wanted to actually write these out in a systematic way, first, I would not be very smart. I would not want to write out a billion equations ever in my life. But if we were, you can imagine I am going to run out of letters in the alphabet. There are only 26 letters in the English alphabet, and multiply that times 2 if you're counting for uppercase and lowercase. And I only know so many alphabets, right? I mean, you know the Greek one, and then there are other alphabets where you know symbols, but the point is you're going to run out of symbols. So there's got to be another way of denoting these scalars than to just write different letters as the notation to describe a scalar. So because of that, people have come up with a different type of notation, and here's what they've come up with. And I think it's very smart because it's an easier way of categorizing each different linear combination. And here's how it works. What they do is they say let's rather than calling this M, just to be, you'll see why I'm going to do this in a minute. Let's call it A. This will be good. So let's say the linear map is called A. Then the coefficients, they're going to still be A's right here, but they're going to add an additional index to each of these coefficients. That index corresponds to which of the components in the codomain we're looking at. So if this is W1, I'm just going to add a 1 in front of every index on these coefficients. So rather than A1, I'm going to have A sub 1, 1. Rather than A2, I'm going to have A sub 1, 2. All the way through A sub n, which is A sub 1, n. To say that these coefficients correspond to the first component of W. And then what we can do is, now that every scalar has two subscript indices, it's very easy to just generalize that, so we don't have to write a new letter for every codomain element. Rather than writing B for the second equation, I can write these as a bunch of A coefficients, where again, the first index will correspond to which element of the codomain we're looking at. This is the second element of the codomain, W2. So we would write A2, 1, then A2, 2, all the way through A2, n. And hopefully you can imagine how the pattern would just generalize. Rather than writing C all the way down to the nth component, you just replace the C's again with A's. A, like this. And again, the first index would correspond to the component of the codomain. So we'd have an M in the first one, and this would be A sub M1, A sub M2, all the way through A sub M, and I guess N. Like this. So by adding another index to each of our scalars, and again, that's not doing anything, that's not changing their properties. All of these are still just real numbers, but it's a way of categorizing them, so each of these indices serves a purpose in this construction right here. And by doing this, what we can do is we can say, all right, rather than writing out a bunch of different equations, we would have, I guess, 1, 2, 3, 4, all the way through m different equations. Let's just rewrite this kind of back in this vector notation that we've had over here. And let's see, maybe I will write it over here. I want to make sure I have room for this. So let's rewrite this equation, but using kind of the notation that we've established so far. So on the right-hand side, I still have my codomain vector W, W1, W2, all the way through Wn, like this. And on the left-hand side, I have this map A acting on the domain vector V. And notice that the map is on the left, right? And that's kind of the notation that we've been using just for a general function. So it's like the map is on the left and then the input is on the right. So I'm still going to have my input vector V on the right. So this is going to be V1, V2 through V sub n, like this. But rather than just writing A, I'm going to say A, this map is uniquely determined by whatever these coefficients are, right? And you can imagine if we had a different linear map, maybe if this was B, that would change the vectors in some different way. Different maps affect vectors in different ways. So a different map would have different coefficients right here. But because we're working with the map A, it has coefficients A sub 1, 1, A sub 1, 2, A sub 1, and all of these coefficients in here are what determine how A affects V and maps it to W. So what we can do is we can say, let's take all of these A coefficients and put them in a grid. Okay, and this is what we have been leading up to, right? So you might be, if you've heard of this, you might see where this is going. But I am going to write a grid, and the grid is just arranged in a way where I'm going to space out each of these coefficients. And I'll show you how to do that. So we see that this V1 right here, we have V1 right here, we have W1 right here. So we're going to want all of the corresponding coefficients that start with an index 1 to be written right here. So I'm going to have A sub 1, 1, A sub 1, 2, all the way through A sub 1, n. And there's not a comma separating these, they're just coefficients with spaces in between them. And then for the second equation, what are the coefficients? Well, we have A21, A22, A23. So A21, A22, dot, 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 all the way through A2n. And this would just continue downwards, all the way through AM1, AM2, AMN, like this. And it's almost like you can imagine if you were to just take a screenshot of this system of equations, replace this with a grid, like this, the locations of the coefficients here are the same as the locations of the coefficients right here. And what we call this grid is a matrix. Okay. So to answer the first question for this video series, or for this video, I should say, what is a matrix? A matrix is a grid of numbers in the literal sense, but it is used to represent a linear map. These maps that we are interested in linear algebra, every linear map can be represented by a grid of scalars, which we call a matrix. Okay. So that's all a matrix is. It is just a way of describing a function that goes between vector spaces that is linear. All right? And so many people, I think, just see it as a grid, but they don't see how this grid represents the linear map. But that's the power of this grid of numbers. It's not this grid by itself, and then we just care about grids all of a sudden. No, it represents this more fundamental object in understanding vector spaces. Okay, so I hope that makes sense. That is what a matrix is. It's a way of representing a linear map. Now, just really quickly too, just to introduce some basic terminology that we're going to hear throughout the rest of this video and the rest of the video series. You can see that even though we've been calling these vectors column vectors because they kind of look like vertical columns, right? But it'd be weird to call this thing just a column, right? It's kind of like there are columns, but it also goes in the horizontal direction, right? So we want to introduce some terminology to describe what this matrix right here. Maybe I'll just write out the matrix over here just to introduce some basic properties of it. So we have A11, A12, all the way through A1n, A21, A22, all the way through A2n. I'm going to try to do this as quickly as possible. AM1, AM2, all the way through AMN. All right. So we've already established that these vertical lines of numbers are called columns, and the same idea applies to the matrix, to this thing called a matrix. So we would ask ourselves, first thing we could ask is how many columns are in this matrix? We could say, or in other words, how many vertical lines of numbers do we see? You say, okay, well, this is the first one, this is the second one, this is the third, the fourth, all the way through the nth. So we would say in this matrix, it has n columns, okay? N vertical lists of numbers. Now, of course, there are also horizontal lists of numbers as well, right? And you might have heard of this. Horizontal lists of numbers like this are called rows. And whenever we talk about a matrix, we are interested in the number of rows it has and the number of columns it has. So we can ask ourselves, this linear map represented by this matrix, how many rows does this matrix have? And we could just count how many rows we would see. We see, okay, this is the first row, this is the second row, the third, the fourth, all the way through the nth row. The amount of rows we have is how many components there are in the codomain. So if we have an m-dimensional codomain, we would say that there are m rows associated with this matrix. All right. And rather than saying this matrix has m rows and n columns, because mathematicians can be lazy. We don't like to say words, a lot of words, even though I am saying a lot of words. There's a compact way of saying that. We could say that this is an m by n matrix. So let me write this out here. This is an m, and the notation that we use to say this compactly is we'll write the number of rows, m, and then a cross, like a time symbol. This is an m by n matrix, where the first number is the number of rows, and the second number is the number of columns. Okay, so that is a compact way of describing a matrix. Now, just to quickly go through some jargon that is almost like a catchphrase for linear algebra before we erase the board, because we're introducing a lot so far. Is you'll hear professors say matrix multiplication is row by column. And it's like this thing that everybody says. And it's like one of the notorious things where students are like, okay, sure, I can do row by column. I can memorize this equation you're giving me. I don't get it at all. Why am I doing this? Why row by column? Why do I care? All right. And let me just try to explain that, probably before erasing the board. Okay. So when we're talking about row by column, the first thing that we would need to do, and when we hear this phrase, row by column, is we can say, all right, I understand how a matrix has rows and columns, but we can also think of vectors as having rows and columns. Now, it might be a little weird, but just bear with me for a second. Clearly, we've been calling these column vectors because they are one column. But we can also imagine that these vectors have associated rows with them. It's just that rather than the rows being horizontal lines of numbers, the row is just one number each. This row is V1, this is V2, this is Vn. Mini rows. Same with this guy over here. So what we could do is we could almost think of a column vector as just a skinny matrix. Where we could say that this would be, how many rows would we have here? We would have n horizontal lines. So this would be an n by 1 matrix. And how many horizontal lines would we have here? Well, there are m components, so this would be an m by 1 matrix. And then again, this would be an m by n matrix. Right. So if we think of vectors as skinny matrices, or just matrices that have where the number of columns is 1, then this will allow us to understand this catchphrase, multiply row by column. Okay. Now, what we can do is we can say, what is another way of saying W1? We could say W1 is the first component of the codomain vector, first element in here, and there's nothing wrong with that. That's perfectly okay. But another way of describing it is that it is in the first horizontal line, the first row, and the first and only column. So this would be the first row and the first column. I want us to keep that in mind, because if we think of W as being the element in the first row in the first column, an easy way to remember how to calculate W, because again, W is calculated from this linear combination right here. An easy way to calculate W is to take we would say, okay, if it's the first row, let's take the first row of here, and if this is the first column, let's take the first and I guess only column of here. Let's take a linear combination of those two by multiplying row by column, and we'll see that that is what this element equals. And then maybe let's actually try to see how that would work. You say, okay, if this is the first row in the first column, I would take A11 times V1 plus A12 times V2 plus A13 times V3 all the way through A1n times Vn. You see how I'm kind of matching them up in a linear combination, taking this row by this column to get this value. And that is exactly what this equation is right here. Let's do it maybe for another example as well, for W2. What would be the row and column of W2? Maybe take a minute to think about that. Assuming you've taken a minute to think about that. It is in the second horizontal line, so the second row and the first and only column. So how would we obtain the equation for W2? How would we obtain this guy right here? Well, we would just take the second row times the first and only column of this vector right here. So A21 times V1, this, plus A22 times V2, this, plus A23 times V3, all the way through plus A2n times Vn. So when we say row by column, we first can just think of what are the indices associated with this vector right here? You say, okay, whatever those indices are, we just take this row in this matrix, multiply it by this one and only column, and that's how we get that corresponding number. So when we say multiply row by column, that is just a quick way of understanding everything that we've built up here. It just so happens that row by column produces this type of equation. It produces all the equations that get used in a matrix, and a matrix gets used as a way of representing a linear map, a function between vector spaces. You see how there's all of this necessary framework that goes into really understanding what these objects are. And if you just get thrown, here's a matrix, do row by column with this times this, and you get this, and that's all you hear, you're not going to understand where it all comes from. This, in the entire last video, is where it all comes from. Okay? So I really hope that makes sense. And maybe just to quickly summarize everything I've said so far in 1 or 2 sentences. A matrix is a representation, a way that we can represent a linear map, a map between vector spaces that's linear, in a grid that has a certain number of rows and a certain number of columns. The way that we apply that linear map on an input function or an input vector to get an output vector is by taking the row and column multiplication and getting the corresponding component going one by one. I hope that makes sense. Okay. Now, assuming that makes sense, and we have answered the first question, what is a matrix? Representation of a linear map. What I want to do next is I want to try to build some intuition by looking at specific matrices. In other words, what we're seeing right here is just a grid, an m by n grid of, it looks like variables, but these would really just be real numbers, right? They're all scalars. So it'd be this grid of numbers. But when we look at that grid of numbers, what does that intuitively represent? After all, we said that intuitively in the last video, a linear map described taking a vector and transforming it, moving it in some way, shape, or form in space. So that's taking that and relating that to a matrix. A matrix should also do the same thing. A matrix intuitively should take a vector, an arrow in space, and move it in some way, shape, or form. So what we're going to be doing, we're going to erase the board, and that's what we're going to spend the rest of the video doing, is we're going to be asking ourselves, when we look at a various grid of numbers, what type of transformation, how does that manipulate a vector in space? How can we see how an arrow in space is transformed? Okay. So I'm going to erase the board, and then we're going to go through that next. Okay. So we have answered the question of what a matrix is, but we might still be wondering, okay, maybe a matrix transforms an arrow in space. It moves an arrow in space in some way, shape, or form. But when I look at a grid of numbers, how do I know what that grid of numbers does to a given vector? And for the remainder of this video, because I am limited to a 2-dimensional board, we're going to be working in R2. And specifically, the functions that we're going to be interested in, the linear maps, are going to have a domain of R2, which means they're going to take in 2-dimensional vectors or 2-dimensional arrows, and they're going to move them to some other 2-dimensional arrow, just so I can draw it on the board. So it's going to go from R2 into R2. All right. But note that this is going to be applicable for really just a general linear map and a general corresponding matrix. That's an m by n matrix. And maybe I'll just put some tick marks. Just kind of making something up right here. And let's suppose, for example, I have a vector in this 2-dimensional space, R2. And this is going to be my domain. And maybe that vector has coordinates 1, 2. So I'll try to draw this as best as possible. This arrow right here, maybe this is a vector v, and if I write it as a column vector, it is 1, 2, like this. And again, the first component would say that it is 1 unit in the positive x direction, and the second component means it's 2 units in the positive y direction. Now, what is a different notation that we can use to describe this vector that we've talked about in this video series? And hopefully the I hat, j hat notation comes to mind, or hopefully that sounds familiar at least. Another way of writing this vectors is to say that this is 1 in the I hat direction plus 2 in the j hat direction. Or again, we called these unit vectors, that's why we put a hat over them to denote that they are unit vectors, or in other words, vectors of unit length, vectors that have a length of 1 unit. And I hat is the unit vector that has a length of 1 unit in the positive x direction, or to the right. And the j hat vector is a vector of unit length that has that points in the positive y direction, 1 unit upwards. So 1 unit to the right plus 2 units upwards. Simple enough, right? Now let's say, supposedly, that I have a linear map and then a corresponding matrix, A, that acts on this vector v. And what I'm interested in is first maybe to see how this vector v transforms, and second is to, what am I trying to say? And the second is to see how can I write the scalars associated with this matrix? How can I write out the numbers in the corresponding grid? So what we can do is we can say, if we're interested in seeing how this linear map acts on this vector right here, let's just use what it means for A to be a linear map. Okay, so let's say that A acts on this vector written out here in unit vector notation. So A takes in 1 I hat plus 2 j hat. Well, what does it mean for A to be linear? What it means is if we have a linear combination of inputs, that will correspond to a linear combination of outputs. 2A times j hat. This is, again, just from the definition of what it means for a map to be linear, right? And what I want to do is not just to write this out, but to establish the importance of this. And this is going to be tying a lot of concepts together that we've been talking about so far. If you remember, we spent a decent amount of time talking about basis vectors, right? Which was a language that we could use to describe a corresponding vector, right? So what we would say is that this vector v, when written in this notation, we would say it's written in the standard basis, or the I hat j hat basis. But we could write this in some other associated basis as well. This is just one language that we can use to write a vector. But let's also remind ourselves that a basis can be used to describe any vector. In other words, since I hat and j hat form a basis in R2, what that tells us is that any vector, any arrow in space that I draw, whether it's this arrow, this little arrow, any of these vectors and any arrow in space that I could possibly draw can be represented by this basis. So in order to see how so here's the next step. In order then to see how any of these vectors gets transformed by a corresponding linear map, all I really have to do is to see how that linear map affects whatever basis I'm working in. And because the standard one to work in is the I hat j hat basis for 2 dimensions, or I hat j hat k hat for 3 dimensions, or whatever it is, then all we have to do, rather than trying to figure out specifics to a corresponding vector, we just have to say, let's figure out what basis the vector is in, see how the linear map transforms this basis, and then however this linear map transforms this basis, that will tell us correspondingly what the output vector needs to be. Let's see how this works, okay? Maybe let me erase some of these arrows to clear up the picture here. So we're only working with our single vector v equals 1, 2. Now, let's suppose that, and I'm actually just, because I'm only going to work in the positive dimension just to keep enough space on the board. This is the domain. Let's maybe write this. This is the domain. And if we were to write out the corresponding codomain, let's suppose that the transformation and how A affects the two basis vectors is it causes both of them to get bigger, but it doesn't cause them to rotate at all. In other words, if we started with I hat, a vector of length 1 in the positive x direction, maybe when this linear map acts on this vector, it causes it to change to maybe 3 times its original size. Maybe it starts like this, and then it grows the vector so it looks like this. Okay? So if that's what it does, we can say that the new, and maybe let's hope the blue marker works. I haven't tried it. If we were to say that, oh, that does not work at all. Yeah. Let's try the green marker. I'm out of colors after this too, so let's really hope this works. Oh, good, it works. So if this green arrow is I hat, a vector of length 1 in the positive x direction, and this green arrow here is j hat, vector length 1 in the y direction. If we were to see how maybe I hat transforms, now let's say that it grows to 3 times its size. When the linear map acts on it, it increases its size by 3 amounts. So if I were to draw tick marks as best as I can, maybe this is the new I hat. It started like this and then it enlarges itself. So this new vector here would no longer be a unit vector because it has 3 units of length. So we would say that this is the linear map A when it acts on I hat. Okay? That is what this corresponding thing is right here. And maybe it has 3 units to the right and 0 units upward. And the original I hat was 1, 0. Now let's go to J. Maybe this starts as 0, 1. And a matrix, or a linear map or matrix, whatever, really they're interchangeable, does not need to grow everything by the same amount. It could, there's nothing wrong with that, but it could grow them by different amounts. Maybe it grows everything horizontally 3 times, makes things 3 times as wide, and maybe it makes things 2 times as tall, or a half a time, 1.5 or 0.5 times as tall. It could be whatever number we want, it doesn't matter. But let's say maybe that it makes it 2 times as tall. So the corresponding, when A acts on J hat, and I hope we can see these colors. I try to avoid colors because I'm not sure how it appears on the whiteboard, but hopefully we can see these colors right here. When A acts on J hat, now it turns it into a vector of 2 associated units of length, okay? So I can write this, and I'll write little equals that this is 0. Actually, let's do this. I want to make it too confusing. Let's say that A acting on J hat is 0, 2. Okay. We say, okay, cool. So we have now established that whatever A does, it seems to make things bigger, right? It takes the horizontal direction, makes it 3 times the original size, takes the vertical direction, makes it 2 times the original size. Now, but what we're really interested in, right, was the question, how does the linear map A act on this arbitrary vector V, 1, 2? Well, let's just apply what we have here into this equation. So A acting on this is going to be this equation. So we still have equals number 1 times A of I hat. What is A of I hat? Well, that was this column vector right here, 3, 0. Plus 2, hopefully I'm not going out of the board too much, times A of J hat. And in A of J hat we said was 0, 2. So we just substitute that in. Like that. And now we can just perform standard vector operations, the operations of a vector space. We can multiply the scalars by vectors. So 1 times 3, 0 is just 3, 0. And then 2 times 0, 2 is 2 times 0 is 0, and then 2 times 2 is 4. and then the vectors add through vector addition. So 3 plus 0 is 3. 0 plus 4 is 4. So what we see is that the output vector is going to just be 3, 4. If I were to, let's see, if I were to draw this on this diagram right here, it would look something like this. This would be A acting on V, giving us 3, 4, like this. Okay. So this is the first main takeaway, is that regardless of what vector you're working with, once you know the basis that vector is written in, and typically it's going to be the standard basis, the I hat, J hat, K hat basis. We have 1 pointing in each positive direction. All you have to do is you have to see how the linear map affects that basis, and then you can, once you see how it affects that basis, then the corresponding output vector is just the linear combination of how the basis transformed. The starting vector was 1 times the old basis plus 2 times the new basis, or sorry, 1 times the old first basis vector plus 2 times the old second basis vector. Now, the resulting output is going to be 1 times the transformed first basis vector plus 2 times the transformed second basis vector. It's still a linear combination of basis vectors. You're just seeing how the basis transforms going from the domain to the codomain. So I hope that makes sense. You only need to really see how a linear map affects a basis, and then from there you can get whatever vector you want on that linear transformation. Okay. Hopefully that makes sense. Now let's keep going though, because we still haven't introduced any grids or any matrices in this whiteboard. This is still all working with A just as a linear map, not a matrix representation. Okay? And I think to do this, what I'd like to do is I'd like to write out this equation in its complete form here. So let's say this is going to be my left-hand side. I'll write this down here, and I know I'm running out of room. So 1 times 3, 0 plus 2 times 0, 2. And that equals 3, 4. Right? So what we can do is we can say, all right, when we were working with the V and W picture in the last whiteboard, these were the various components. And we said that these components in the codomain were obtained by linear combinations in the domain. So let's write out this single vector equation in component form, starting with the top component. So if we were to look at the top component, we would have 1 times 3 plus 2 times 0. And what does that equal? 3. All right. And then same thing with the bottom component. 1 times 0, and I hope we can see this, plus 2 times 2 equals 4. All right. Now let's keep in mind what is going on here, because before we had all symbols, now we have specific numbers. So we want to make sure we understand what each number means. All right. So we said every component of the codomain depends on every component of the corresponding domain. And we would really just need to ask ourselves, well, what is the vector in the domain? Well, the vector in the domain was 1, 2. That's what this original arrow was right here. This black, and maybe I should even draw to make this more. That arrow goes to that. Right. So 1 and 2 are the elements of the domain. And to obtain this element in the codomain, to obtain 3, we had to take a linear combination of 1 and 2. But notice that 1 and 2 remain consistent throughout each of these two equations. And if we had n different equations, 1 and 2 would be consistent in each of those n different equations. So that tells us that let's try to write this now back in vector notation, where this 3, 4 is the output vector, the codomain. We know 1, 2 is the input vector. And now we just need to write out the corresponding matrix. And what was the way that we could kind of represent the matrix? Well, we said that if these were the domain elements, then these things over here were the scalars that were multiplying, the things in the linear combination of the domain elements. So if we were to form a grid around this guy, this guy, this guy, and this guy, you can imagine that we could put them in a m by n grid, where m is 2 and n is 2, or in other words, a 2 by 2 grid, where these are going to be the components of the grid. So it's going to be 3, 0, 0, 2, like this. Okay. So what we have just done, because we're kind of doing a decent amount of stuff really quickly, is we are showing that by taking a vector in the domain, rewriting it as a vector in the codomain, we can correspondingly write out what the matrix has to be. It is this matrix 3, 0, 0, 2. Now this might sound relatively familiar, because after all, what was A when acted on I hat? 3, 0, 3, 0. And what was A when acted on by J hat? 0, 2, 0, 2. And it turns out that is not a coincidence. And this is probably one of the biggest ways that we can understand a matrix. And when we look at a grid of numbers, what are we actually looking at? What we are looking at is every column of this matrix. In this case, there are only 2 columns because we're working in 2 dimensions. But if we're working in n dimensions, there are going to be n of these vertical columns. Every column tells us how the standard basis vectors got changed. Let's ask ourselves again, how did the standard basis vectors I hat and j hat get changed in this specific linear transformation? Well, in this one, I hat got enlarged to 3, 0, 3 times its size, and j hat got enlarged to 2 times its size. So I hat moved to 3, 0, and 0, 2. Or I hat moved to 3, 0, and j hat moved to 0, 2. So when we look at a grid of numbers, what we are really looking at is specifically how the standard basis transforms. And again, just to make one more step, if we know how the standard basis transforms, then we know how any vector transforms, because we're working with a linear transformation. A vector that takes some input and just produces a linear combination of outputs where the matrix acts only on how the basis, where I should say the matrix acts only on the basis vectors. Okay. So I hope that makes sense, that we can read a matrix, read a grid of numbers as the transformed coordinates of our starting basis. All right. Now that's kind of a lot to take in, so I hope that makes sense. And feel free to pause the video if parts of this are confusing. I seem to be out of room again, and I tend to do that relatively often. So we're going to erase the board one more time, and I know this video is probably going to be a little bit longer, but I really think it's worth it for such an important topic. I want to finish the video off with going through specific examples of matrices. In other words, when we look at specific types of matrices, how can we visualize how they transform based off of what we just said? So I'm going to erase the board, and then we're going to go through some examples to finish off. Okay, so now to finish out the video, we're just going to go through a couple of examples of types of transformations and try to gain an understanding for what the corresponding matrix will look like. So I want to start kind of with what we were doing in the last whiteboard, which are matrices called dilation matrices. This is a fancy way of just saying matrices which enlarge or shrink every vector. And matrices that are pure, like stretching matrices. And a dilation matrix, we're going to be thinking of a matrix which only stretches or shrinks vectors. In other words, that is the only transformation that occurs. There's no rotations at all or any other type of transformation. So if we think of a matrix that only stretches the vectors, and maybe we're only going to work in 2 dimensions. So we're thinking how a matrix transforms only I hat and j hat. We would ask ourselves, how would that happen? And I really would recommend take a minute to pause the video to think about that. Okay, assuming we have paused. So I want to start with this because this is what we were doing in the last whiteboard. But we can imagine that if the I hat vector gets transformed, so in other words, I hat is the 1, 0 vector, and it gets either it gets stretched out or it shrinks, but it doesn't rotate at all. That means it's, regardless of how its length changes, it's always going to be pointing purely in the horizontal direction. In other words, this bottom component is always going to be 0, and the only component that changes is the top component. And the number that it changes to, if it's larger than 1, it gets stretched. If it's smaller than 1, it shrinks. In the general case, it could get scaled by some scalar, lambda. And maybe when the matrix acts on it, it goes to lambda 0. So we would write the first column of this matrix as how I hat gets transformed to lambda 0. And you can imagine the same thing is going to happen with j hat, right? If j hat starts as 0, 1, and all we do is we scale it, we're not changing its direction. It will only point in the vertical direction, and it's only going to change its size. So the horizontal component's always going to be 0, and this 1 will get changed to some additional scalar, which we would call mu. So we would write 0 mu, like this. Okay. So let's just take a minute to notice this. This is a general stretching or shrinking matrix. And the most general type of matrix that we could come up with, which only stretches or shrinks a given vector, will always have 0 in these positions right here, and we'll have some scalars right here. These types of matrices are called diagonal matrices. And a diagonal matrix, I should probably introduce a little more terminology. If we were to imagine a diagonal line pointing from the top left to the bottom right, and maybe I'll even just draw it like that, that is called the main diagonal of the matrix. So here we would say that if we have some scalars on the main diagonal and everywhere else we have a 0, then that would be called a diagonal matrix. This is the case for a 2-dimensional diagonal matrix. Let me maybe just quickly draw out a 3-dimensional diagonal matrix. So lambda, mu, nu, and then we have zeros everywhere else. This would be a 3-dimensional diagonal matrix. And then you can imagine n-dimensional diagonal matrix. N different scalars. They don't have to be different, they could be the same, but n scalars along the main diagonal and zeros everywhere else. The zeros being everywhere else is really the key part. Okay. So in general, whenever we see a diagonal matrix, a matrix of this form, that will always correspond to a matrix which only shrinks or stretches out a given vector. And in other words, it will not change the direction that it is pointing in. Okay. Hopefully that makes sense. Now let's keep going, because I've mentioned a lot about changing direction or not changing direction. Let's now move on to matrices where their only job is to change the direction of a vector. So in other words, the vector's length now is going to stay the same, but only its direction is going to change. In other words, we can think of this as a rotation matrix. So let's write that out. So we have matrices that are called rotation matrices. Now, what we can imagine too is we can call on our knowledge of the unit circle, which hopefully we are familiar with. And the reason why I want to specify the unit circle, and let me even just draw this real quick, is because our standard basis vectors I hat and j hat lie on the unit circle. So if we were to draw this, pretend that's the unit circle, where the horizontal arrow is I hat, and the vertical arrow, which I tried to draw, is j hat. then if you were to imagine that a matrix only rotates, then these vectors right here are going to still be on the unit circle after the transformation. It's just that they're not going to be, I hat's not going to be purely horizontal and j hat's not going to be purely vertical. Maybe the new I hat gets rotated, and I'll try to draw it with like a dotted line. Maybe the new I hat gets moved to here, and maybe the new j hat gets moved over to here. So we can imagine let's do this. We can imagine a rotation by a certain angle, like this. And maybe what we can do is we can provide a name to that angle. And we can call that angle theta. And the reason why I'm using the unit circle here is to try to remind ourselves of another type of coordinate system besides the x and y coordinate system. This would be theta that's used in the polar coordinate system, right? So let's call on our knowledge of the polar coordinate system to determine how are the new I hat and j hat transformed if they're rotated counterclockwise by an angle theta. Well, let's see here. I hat is going to have a new x component of, it's going to be the adjacent over hypotenuse, or in other words of saying that is the cosine of theta. So maybe I'll even just write this. New I hat is going to have a horizontal component of cosine theta. This is just going back to trigonometry, right? And a new vertical component of sine theta. All right, I'm going through this quickly because hopefully we've seen this before. But that's what the x and y coordinates of this dotted arrow right here are going to be. Let's do the same thing with the transformed j hat. So the new j hat is going to have an x component that is now in the negative direction, right? Or if we were to draw out, it would be pointing a little bit to the left and still up. What would be the negative x component right here? Well, what we could do is we could, let's see, if this angle is theta, that means this is going to be theta. So this is going to be theta, using properties of geometry, right? And the negative component right here is going to be the opposite over the hypotenuse if theta is this angle up here. And I really hope you can see that. I don't know if you can. Theta is the upper angle in the triangle. So if the horizontal component is the opposite of theta, then it's going to have a negative value first, but then it's going to be sine theta. Let's make theta a little better. And then now let's look at the new y component. What is this vertical distance right here on the dotted arrow? Well, that's going to be adjacent over hypotenuse, and it's in the positive direction, so we have a plus sign and then cosine theta. All right. So now what we've done is we say, okay, we have seen how I hat and j hat transform. Let's just put them in a matrix now. So a rotation matrix, and this is what I'm trying to get at, will always have, the most general rotation matrix will be a matrix of this form right here. So it's going to be, at least in two dimensions, it's going to be cosine theta, sine theta, right? The first column of the matrix tells us how the I hat vector transforms. And then the second column is going to tell us how the j hat vector transforms. So then we're going to have negative sine theta, cosine theta. And again, I should specify too, this is if our rotation is counterclockwise, going from here to here, right? If it was clockwise, going from here maybe to here, then what we're going to see is that there is going to be a sign change. Not literally the function sign, but the negative sign is going to move, right? Depending on where the new dotted arrows end up on the unit circle. Right? So a matrix that only rotates, does not increase the length or decrease the length of any vector, will have this form right here. Let's move on now to one final example, and I want to keep this video as short as possible, but let's look at translations. And for the people that are familiar with linear algebra, they might be raising their eyebrows right now to say, why are we talking about translations? bear with me. I'm trying to make a point right here for those of you who know what I'm about to get at. But for those of us who have not, are still thinking about translations, or thinking about translations in the context of linear algebra for the first time, let's imagine what a translation will do to an arrow in space. So let's maybe put a grid down here. And let's say I have the same starting vector, v, which is 1, 2. And I want to come up with a transformation that translates it, or in other words, it doesn't change the length, and it does not change the direction. So maybe it has the same length, pointing in the same direction, and all I'm doing when I'm translating it is I am moving that vector to some new location in space, while keeping the same length and direction. So maybe after the transformation, maybe now the vector is moved to over here, before, after. You can hopefully imagine what that visual picture would look like that. And maybe if it moves, I don't know, 3 units to the right, that would say that this would be, let's see, that would be 3 plus 1, which is 4, and then still 2 in the positive direction. So maybe this new v right here, new v. I have a lot of arrows, but old, new. New v is going to be 1, 2 plus 3, 0, which is 4, 2, like this. What would the matrix be that corresponds to a translation? And take a minute to think about this. Okay, assuming you've taken a minute to think about this. I try to not introduce too many trick questions. Unfortunately, this was a trick question. But I'm not trying to put you on the spot, too. I mean, it's also a video, right? I mean, you're not calling you out in person. I'm not trying to do that. It turns out that you can't write a translation with a matrix. I'd be like, why, right? You can do this with these stretching matrices, these rotation matrices. Why not a translation? And to see why, and this is something that might be a little weird at first, but we just got to go back to the properties of a vector space. What are some of the fundamental things that are true about all vector spaces to see why? So one of the properties of a vector space is that when, let's say, or I should say, one of the properties when talking about linear functions that map between vector spaces. So let's be specific here. If I have a map M that goes from Rn to Rm, then if I were to act M on the 0 vector in Rn, so in other words, M acts on the 0 vector in Rn, that needs to map to the corresponding 0 vector in Rm. So this would be a column vector n of n numbers long, where each of those numbers are 0. And this would be a column vector of m numbers long, where each of those m numbers are 0. This is a fundamental property that needs to be satisfied with linear maps. To understand, maybe if that's not immediately obvious too, there are, I'd recommend going to the group theory playlist. It turns out we could think of these linear maps as homomorphisms, and one property of group homomorphisms is that the identity element needs to map to the identity element, but I don't want to make that a requirement, but that's kind of we go over the general reason why in that video series on why this needs to be true. But hopefully this somewhat makes sense, and that the identity in the domain needs to map to the identity in the codomain, and if it does, then you can probably see why a translation won't work. It seems like this translation taking any vector from here and moving it to the right 3, we just ask ourselves, okay, well, how is that going to affect the identity, or sorry, the 0 vector, the origin? Well, if it starts at 0, 0, and then it moves it to the right by 3, the output is going to be 3 to the right, 0. Or in other words, if we start with 0, 0, the 0 vector, and then we add 3 to the right, we're going to end up with 3, 0, right? So what we're seeing is that with a translation as a type of operation, it takes in the identity, or sorry, I'm thinking the identity element from group 2. It takes in the 0 vector, but it spits out the non-zero vector. And because this property is not allowed for linear maps, therefore translations are not considered linear transformations. Now, I want to be very clear too. Is a translation a type of mapping, a type of function, a type of transformation? Absolutely. And I'm not trying to say translations don't exist in the real world or the mathematical world. Because again, an arbitrary map just takes every element in the domain and maps it to a unique element in the codomain. And isn't it true that every element in the domain can get shifted by a little bit, by some amount, to map to another vector in the codomain? The answer is yes, every vector can get shifted over. So a translation is a type of function. However, it is not a linear function. So it does not have it is not a function that has the property that satisfies what it means to be linear. And because we are interested in studying linear algebra, we are interested in linear functions, linear maps. That's the whole title of the section. So therefore, we're not really going to be interested in translations. Okay? And I want to make that clear very early on. Now, one more thing that I want to make clear too, or maybe two more things. I promise I'm almost done. First is that these matrices, these dilation, these rotation matrices, these are matrices where the only effect is to stretch, or the only effect is to rotate. But you could have combinations of these two. You could have maybe a vector that starts like this, purely vertical, and then maybe after the transformation it gets rotated and doubles its length. You could have a matrix that is a combination of both dilation and rotation matrices. It's just that in the case where you have a matrix that combines multiple of these effects, it won't have an immediate structure like the ones right here. These are relatively simple to write out their structure, which is why I wanted to include them. So that's the first thing, that transformations are not limited to only one of these types. You can have combinations of types for a general type of linear transformation. And then the second thing is that these are not the only types. Pointing over here, I should be. Dilation and rotation matrices aren't the only types. There's some other examples like reflection matrices, where every arrow in space gets reflected across a certain axis, kind of like a mirror. There are also matrices called shear matrices, and that's where you keep one basis vector the same, and then you kind of shift the other basis vector. How do I describe this? It would probably be best with numbers, but maybe if this was your starting basis, a shear matrix might keep the right arrow pointing to the right, but it would take the vertical arrow, and rather than keeping it vertical, it would point it diagonally like this. So the only change in the basis would go from here to here, and we call that a shear matrix. So point is, there are different types of transformations than the ones that I just mentioned, but these I think are the easiest to visualize intuitively, which is why I wanted to cover these. But we covered a lot in this video, right? So thanks so much for watching. I really do hope this made sense. And yeah, I'm happy to be back making videos. The goal is to try to be making 1 or 2 a week consistently going forward. So yeah, thanks so much for watching, and I will hopefully see you in the next one.